All right. Hello. My name is Professor Dan Chavas. I'm a professor at Purdue University, study atmospheric science. And so what I'll be talking to you today is a concept that hopefully you've heard before called the jet stream. What is the jet stream? So I'm actually starting you off here with a computer model visualization of our atmosphere. We're looking at the colors, our wind speed at about 12 kilometers above the surface. So way up above your head. And you'll notice these yellow and red streaks that are swirling and moving from left to right. And those reds in particular are wind speeds up to something like 170 miles per hour. So very fast. Think about you drive on the highway at, say, 60, 70 miles an hour. So you see these bands of air moving very, very quickly. That is the jet stream. So we're going to talk about that here. So hopefully you've heard of the jet stream, in particular from your local TV meteorologist on TV. They like to talk about the jet stream, and that's because it's really very important for determining the weather in our everyday lives. So you might see a weather map like this showing cool and warm. And here the jet stream is labeled. And I put some white dashed arrows here to give you a sense. There's air moving from west to east here and a little bit south and north as well along the jet stream, where it seems to be separating colder and warmer air. So we're going to talk a little bit first about our Earth, so we can get oriented here. So hopefully you've thought about or learned at some point, we think about space on the surface of the Earth and in our atmosphere in terms of latitude and longitude. So on the left is lines of latitude from 0 at the equator down to 90 at the South Pole, 90 degrees south, and then 90 degrees north. Latitude is the North Pole. And we typically break this up. We say the northern hemisphere and the southern hemisphere. So we're here in the northern hemisphere. Here's Indiana. And then on the right is longitude, which we won't talk about, just to remind you. Longitude is moving east-west. Latitude is moving north-south. And so we often break up the Earth's, or kind of thinking about space or moving in our atmosphere by latitude into different regions. So near the equator at very low latitudes, we think of as tropical, as the tropics. And then to a little bit higher latitude, getting close to 30 degrees north or south, are the subtropics. Between 30 and 60 degrees north or south are what we call the mid-latitudes. That's where we live. And then in high latitudes are the polar, subpolar, and polar regions. So the Arctic in the northern hemisphere and Antarctic in the southern hemisphere. So we're going to we'll talk a little bit about the mid-latitudes, which is where we live and where the jet stream generally lives as well. So we're going to go back to our movie, which hopefully you've had a chance to gaze at. So we'll take a little bit more time. So I've marked the equator on here. So we're thinking about a globe. We've sort of unwrapped the globe and spread it out into a rectangular map. And so we can see the whole Earth at once. And so again, the color shading, it's noted at the bottom, is wind speed at about 12 kilometers altitude, where the yellows and the reds are the fastest winds. And then actually the white shading, if you're interested, is wind speed at the surface. But we're just going to talk about the colors at high altitude, which is where our jet stream is. So you'll notice here, so again, these streaks, if you just kind of first notice that things are moving west to east, you're actually seeing the jet stream and also the movement of air in general. The jet stream itself actually moves from west to east. So the jet stream is a narrow band of relatively strong winds directed from west to east in each hemisphere. So it's located in the mid-latitudes, can move north and south, but generally in the mid-latitudes with the strongest winds approximately 12 kilometers above the surface. So again, thinking this is way above your head, but this is where, say, airplanes fly. So if you've ever flown from Has anyone here ever flown in an airplane and gone towards the west or towards the east? You have any idea which way is it? If you were to fly to, say, Europe, so to the east and back, which direction would you go? Do you think you'd go faster? Would take less time? So it's going to the east, because in that case, when you fly from west to east, you're flying along with the jet stream. So the jet stream is giving you a tailwind. Whereas when you fly from east to west, you have to fight the jet stream. It's a headwind. So the other thing I want you to notice is that the jet stream meanders. It doesn't flow purely west to east. You can see it's broken up into these bands. You may have noticed there's differences between the northern and the southern hemisphere as well. But the big thing I want to highlight here is it has these undulations in it that move north and south, and there's variations as it moves from west to east. So the jet stream meanders. And so that's important that it meanders because the jet stream, as we showed before, it separates warmer air to the south from colder air to the north in the northern hemisphere. There's a big temperature difference across the jet stream, you'll notice. And so when the jet stream undulates north and south, it moves this cold and warm air around, causing our weather to be always changing. And in the summertime, we're generally in the warm side of the jet stream. In the wintertime, we're generally on the cold side of the jet stream. And in spring and fall, we may be on either side of the jet stream at any given time. So it's really important for our weather changing both during the course of a year, but also from day to day or week to week. And importantly, the jet stream also brings weather systems, low and high pressure weather systems, which you also probably have seen on TV when they talk about the weather. So here's an example. There's the jet stream. This L is for a low pressure system, usually has clouds and precipitation with it. And then high pressure systems typically have clear skies. So it's really important not just for temperature, but also for rain or snow or here even ice, things like that. So why does the jet stream exist? So we're going to talk a little bit. I'll give you an intro into what creates the jet stream. But there's really two basic ingredients that you need to create a jet stream on our planet. One is the rotation of the Earth. We are on a rotating planet. And then the second is there's the north-south differences in temperature. So we're going to talk about these one by one here. So let's start with the rotation of the Earth. So the thing you may not realize is that right now you are actually moving incredibly fast in space, unless you're standing on the North Pole right now, which I'm assuming you're not, or the South Pole. This is a view from space if you were looking down at Earth, spinning about 1 day every second, or I guess spinning around every second, which is equivalent to 1 day. So if you're standing at the equator, you're moving at approximately 1,000 miles an hour in space, which is really fast. An airplane flies at, say, 500 miles an hour. So you're actually moving incredibly fast in space if you were at the equator especially. Here in Indiana, about 40 degrees north, you're moving at around 350 miles per hour. And of course, you don't realize that, do you? So why don't we notice this? Why doesn't the wind just blow us away? So the atmosphere is also moving at that speed, but then the wind is blowing relative to that. So we observe everything around us relative to the Earth's rotation. When we feel the wind blowing at 5 miles per hour, for example, it's actually relative to the rotation of the Earth. The atmosphere is also adjusted to that rotation. So what this means is when we say relative to the Earth's rotation, a way of saying this is that we live in a reference frame that is rotating with the Earth. So what's shown on the screen right now, this Earth spinning, is the reference frame looking from outer space where you're not moving and you're just seeing the Earth spin below you. But we live on the Earth that's rotating. So our reference frame is rotating with the Earth. It's like our brain has and our atmosphere doesn't notice that the Earth is spinning in some sense. And so a picture here is of a car. If you were driving in a car, watching everything around you go by you, that's in a reference frame moving with the car. So this is an important idea that you're going to get to explore a little bit. Okay, so that's the rotation of the Earth. It's really important. We're not going to go into the details of it, but it's an important ingredient to create a jet stream. The other ingredient is the north-south difference in temperature, which we already mentioned, but we're going to talk about a bit more. So in general, on Earth, it gets colder moving from the equator towards the poles. So it's warmer at low latitudes because there's more sunshine there on average during the course of the year. The sun shines directly overhead for much of the year at the equator. When you go to high latitudes, you get much less sunshine, and so it gets much colder. So the jet stream is superimposed on top of this. Here's our pink arrows. Notice that there's this north-south temperature difference across the jet stream. That's where it's hotter at lower latitudes and colder at higher latitudes. And in general, a larger temperature difference gives you a faster jet stream, meaning stronger winds in the jet stream. So something we're going to come back to. So those are the two ingredients that you need. It's all you need to create a jet stream on our planet. And what's pretty cool is as you're going to see, we can actually replicate these two ingredients in a tank of water that is rotating on a table. So that is on a rotating table. And a picture of this is shown on the right. It's an experimental tank that in person I would do a demo for, but you'll get to see a video of, where you can actually put a bucket of ice at the center to create a temperature difference across the water in this tank that's rotating. And so to note is that the rotating tank, the rotation of the tank or the table mimics the effect of the rotation of the Earth. This is what we call the Coriolis effect. So this is why the rotation matters. I'm not going to talk about exactly why here. But these two things you can create in a tank, which means you can create a jet stream in a tank, which is pretty awesome. So you'll get to see this. Okay, so we just want to talk about one more step here because the Earth's axis is tilted, it means that if there may be times where one hemisphere is pointing towards the sun, and when that happens, the sun shines more directly overhead. So this is summer. So it's shown here as the rotation of the Earth around the sun, or the revolution of the Earth around the sun with the axis. So June 21st is the summer solstice. You'll notice the northern hemisphere is pointing, here's where we are, is pointing more directly towards the sun, which means you get more sunlight. It's not that you're literally closer to the sun, it's that you are more directly facing the sun, so you get more direct sunlight for longer. And this is what we call summer. And it's warmer, and then when you're pointing away, which is on the left side here, and December is winter, that's winter. You're getting less sunlight. So the tilt of the axis of the Earth creates this seasonal cycle of summer, winter, summer, fall, winter, spring. So what does that look like? We can actually look using data at how does temperature change with the seasons. So you know this intuitively. You know when it's summertime, it's warmer, and it's winter, it's cold, and in between, it's something in between. But we can actually see this for the whole Earth. This is what you're looking at here is 22 years of, we're just looking at sea surface temperatures, so temperatures of the ocean surface from 1985 to 2007, and you're seeing about 1 month, I've cut this off to be just about a couple of years here. So it's about 1 year every, we'll say roughly 5 seconds. And the red means warmer. So in the northern hemisphere summer, the reds shift to the north as things warm up on the northern hemisphere and cool off in the southern hemisphere. And then the reverse happens in southern hemisphere summer, northern hemisphere winter. Is the warm air, the warm surface and warm air moves, it looks like it's moving north and south with the seasons. It's almost like the planet is breathing in some sense. So that's how temperatures change with seasons. And so a question is, could this affect the jet stream? If you're changing where it's warmer or colder, might that change how the temperature differences between the low and high latitudes? Maybe this could affect the jet stream. So this is something you need to explore in lab time. So you're going to use data to look at the relationship between the jet stream and temperatures on Earth. So questions you're going to get to answer and think about is, how does temperature vary in the vicinity of the jet stream? Which you've gotten to see pictures of, but you get to see with your own hands and eyes, I guess. Does the jet stream change from season to season, particularly between winter and summer in each hemisphere? And in which season do you think the jet stream is the strongest? Which maybe you could guess based on what you've learned so far, propose a hypothesis, and then you can test that when you look at the data. So you're going to get to see that. All right. Thank you very much.